Lesson 20 is about rational functions. In this video, we'll cover the first part of Lesson 20. To understand what a rational function is, we must recall what a polynomial function is. Remember that polynomial functions look something like these. The third equation is an example of a factored polynomial. Now, a rational function is a function that can be expressed as one polynomial divided by another polynomial. So here are some different examples of rational functions. Since fractions are involved, it's not surprising that rational functions are going to be a little more complicated than polynomial functions. For one thing, rational functions usually have asymptotes. Before we begin analyzing rational functions, we're going to do a little bit of algebra review. We're going to talk about things such as adding and subtracting fractions, multiplying and dividing fractions, and solving fractional equations. In example 1, we are given two rational functions, f and g. As you take a look at the directions, you will see that what we're supposed to do is subtract these two functions to create a new function, function r. Then in part b, we'll divide the two functions to create function s. Here's how we start to write the equation of function r. Recall that when we add or subtract two fractions, the fractions' denominators must be the same. If they are not the same, we have to try to create a common denominator. We always look for the least common denominator. And if the denominators have no common factors, then the LCD is just going to be the product of the two denominators. The way we build the common denominators is to take each fraction and see what factor is missing in the denominator. Then we multiply both numerator and denominator by that factor. That way we're multiplying the fraction really by 1. And if you multiply something by 1, it doesn't change it. It just changes the way it looks. So here's what we get for r of x. Notice that I multiplied the numerators together, but I did not multiply out the denominators. The reason why is because when we finally subtract these two fractions, we want to combine the terms in the numerator. But the denominator is just going to stay the same. When we subtract these fractions, we subtract the numerators and put the result over the common denominator. So there's no need to multiply the denominator out. So here's what we get when we subtract. Notice that when I subtracted, I had to subtract both the 2x and the plus 6. Forgetting to distribute the minus sign is the most common mistake I see students make when they subtract two fractions, if the second fraction has multiple terms in the numerator. Finally, I'll combine like terms in the numerator. So minus 2x minus x minus 2 more x is minus 5x. And the 2 minus 6 gives me a negative 4. Next, we need to divide the two functions to come up with the equation of function s. When multiplying or dividing fractions, you don't need a common denominator. However, since we are dividing, we need to apply the division rule. That just means we take the second fraction, we invert it, and then we multiply the two fractions together. When multiplying fractions, we just multiply the numerators together and multiply the denominators together. If we want, we can leave the function in factored form, or I suppose we could multiply the numerator and denominator out. Which way we want the final answer expressed depends upon the problem. Here it doesn't really matter, but in future problems, sometimes it's better to have the numerator and denominator factored, other times multiplied out. This information here kind of summarizes what we did to work out parts A and B. Now we're ready for example 2. This one has us both add and subtract fractions to create the equation of a new function. Why don't you pause the video and try to do this problem yourself? And then after you're done, then you can resume the video and see how I did it. First, I'll replace the f of t, g of t, and h of t with their three outputs. So this is the equation of r of t. To add and subtract the fractions, we want to find the least common denominator. But to do that, we need to factor the denominator of the third fraction. So the LCD consists of all the factors we see in the denominator. We see the number 2, the variable t, and we see t plus 3. So all three of those multiplied together give me the LCD. The first fraction lacks both the factor of 2 and the factor of t plus 3. So we'll multiply both numerator and denominator by those. The second fraction needs both 2 and t as factors in its denominator. So again, we'll multiply both numerator and denominator by them so that we're multiplying the fraction by 1, not changing it. The third fraction is missing just the factor of t in the denominator. So we multiply numerator and denominator by t. As we continue, we need to be careful. Here, let's do this multiplication. 2 times 2 is 4, and in the denominator, I just rewrote the factors. For the second fraction, t times 2t is just 2t squared in the numerator. And again, in the denominator, I'm just reordering the factors. For the last fraction, when I multiply t plus 1 times t, I get t squared plus t. And again, just writing down the factors of the denominator. Notice that I haven't yet added or subtracted the fractions. That's because I just finished getting a common denominator for all three fractions. So I'll add the numerators of the first two fractions, and then I'll subtract the numerator of the third fraction, remembering to distribute that minus sign. All this is put over the LCD. Finally, I'll combine like terms. When I subtract the t squared terms, that just gives me 1t squared. And when I subtract 4t minus t, that's 3t. And I still have that 12 at the end. And then I'll copy down the denominator. And this is my final answer. Notice that when I add and subtract fractions, I rarely multiply the factors of the denominator together. Better to leave them factored usually. That's it for this page. Now on to the next. In example number 3, we're supposed to take the right-hand side of the function and write it as a single fraction. Since 2 is just an integer, we need to make it into a fraction, call it 2 over 1, and now we have two fractions that we can subtract. The LCD is just x minus 4, and the second fraction already has that denominator. So we just take the first fraction and multiply both numerator and denominator by x minus 4. To get the new numerator of the first fraction, let's multiply the 2 times the x minus 4. Now pause the video and subtract these two fractions. When you're done, unpause and see if you come up with the same thing that I did. Okay, here's what I came up with. Did you get the same thing? Did you remember to subtract both the x and the 1? The next few problems are a little different. We're going to be solving rational equations. A rational equation is one in which a variable appears in the denominator of a fraction. In example 4, we're given the equation of function f, and the directions say we're supposed to find the inputs that cause the output to be 4/5. If we use algebra to do this, we have to solve a rational equation. One way to solve rational equations is to find the LCD, but to use it differently than if we're going to add or subtract fractions. Instead, we will multiply each side of the equation by the LCD. We're allowed to do this because we have an equation. If you do something to one side of the equation and do the same thing to the other side of the equation, you keep it in balance. Now the reason why we do this is so that we can cancel common factors in the different fractions. Let's do that with this equation and see how it works. The LCD is 5 times x plus 3, so we multiply 5 times x plus 3 times the left-hand side and the right-hand side. Notice that as we do this, we're not multiplying by 5 times x plus 3 divided by itself. It's 5 times x plus 3 over 1. This is an extremely important difference because what it allows us to do now is to cancel common factors. Notice on the left-hand side, I can cancel the x plus 3's, and on the right-hand side, I can cancel the 5's. This leaves me with a fraction on each side with 1's in the denominator, which means I don't even need to write them as fractions. What's left is a linear equation. I'll distribute the 5 and the 4 through the parentheses. Then I'll subtract 4x from each side and add 10 to each side. This means that the input is 22 that makes the output 4/5. Okay, in example 5, we have two functions and we're supposed to find the inputs x that cause the function's outputs to be equal to each other. So we're just going to take the output for each, set them equal, and this gives us a rational equation to solve for x. The denominators of the two fractions have no common factors, so the LCD is x times x minus 1. So we multiply each side of the equation by the LCD. Notice that since the right-hand side of the equation has two terms, we must multiply the LCD times both of them. On the left-hand side, I'm going to put the x times x minus 1 over 1 and then cancel x from the numerator to the denominator. This will just give me x minus 1 times 5. On the right-hand side, I'll distribute. So on the left-hand side of the equation, I get 5x minus 5. When I multiply here, I'll put the x times x minus 1 over 1, then cancel the x minus 1's. This gives me x squared over 1. For the second term of the equation, 1 times x distributed through to the x minus 1 gives me x squared minus x. So we have this. So our work has turned the rational equation into a quadratic equation. When we solve quadratic equations, it's nice to get 0 on one side. So I'm going to subtract 5x and add 5 to each side. This is the same thing as 2x squared minus 6x plus 5 equals 0. It doesn't appear that the left-hand side will factor, so I'm going to use the quadratic formula. A equals 2, B equals negative 6, C equals 5. Let's plug those numbers in and see what we come up with. First, let's do a little bit of arithmetic. I can do the subtraction inside the radical, but notice the square root of negative 4 is undefined. We can't take the square root of a negative number. What that means is that the equation has no real solutions. So the answer to the question is, there is no input that causes these two functions to have the same output. Now we're ready for example 6. To do this problem, we have to remember what the zeros of a function refer to. Remember, the zeros of the function are inputs that make the output of the function equal to 0. So to find them, we'll take the output of the function, the fraction, we'll set it equal to 0, and then we'll solve for x. This equation isn't nearly as hard to solve as the last. We'll multiply each side of the equation by the denominator x squared minus 9. On the left-hand side, we'll put x squared minus 9 over 1 and cancel. On the right-hand side, 0 times x squared minus 9 just stays 0. So pretty quickly, our algebra turned the rational equation into a quadratic equation. And this quadratic equation is pretty simple to solve because we can factor the left-hand side. The left-hand side is going to factor like this. We can see that because we were looking for a sum of negative 5 and a product of negative 6. And the two numbers that we want to use are negative 6 and plus 1. Now we use the zero product rule. We get to set both factors equal to 0. Solving each of these equations is easy. We get x equals 6 or x equals negative 1. Now, we should make sure that the numbers that we found are in the domain of the original function. If we plug 6 in for x, we won't be dividing by 0. The same thing for negative 1. The only numbers we couldn't use as inputs into r are 3 and negative 3. So the zeros of function r are 6 and negative 1. Now this is the end of the first part of the Lesson 20 video. A second part will get to the analysis of rational functions. But remember, try some of the homework problems at the end of this lesson. When you see this right here, that just means you can try problems up through number 7 at the end of the notes. By this evening, I'll try to have uploaded a pilot and answer key video so you can check your answers.